with some symbols and fair machine learning.
Okay, well, thank you so much. Thank you, Lalita, for organizing this. Thank you, Adam, for the support. And today I'm going to talk about information theory intersection with fair machine learning. Hopefully convince you that this intersection gives you a set that is non-empty. And the goal of the talk today is that if you're an information theorist in the room, to maybe motivate you to look at some of the tools in problems in fair machine learning. And if you're interested in this area, to maybe take a look at some of what information theory has to offer. And it can give you some fundamental insight in fairness. So the results that I'm going to talk about today were mostly done by this amazing group of people here. Like a lot of the results were done by Lisa, who's a student at the Harvard College, Sean and Hao, PhD students, Burke, who is a postdoc at Circus, and Salman, who is a grad student at MIT. And in the latter half of the talk, a lot of the results were done with my amazing collaborators at IBM, Dennis, Kush, Karthi, and Banu. And here's the agenda for today. I'm going to start with a brief motivation for fairness. I think I might be preaching to the choir here. I know a lot of people in this room are interested in this problem. But if you already heard this, just sit back, relax, and enjoy this time after lunch to hear something you already know. Then I'm going to talk about a few words on modeling and assumptions and some of the temptations that information theorists might have when you're working on this problem. This is something I tell my grad students. Then I'm going to define some group fairness metrics. How do we measure fairness in practice? This is one collection of metrics to do that. Then talk about the meat of this talk, which is the role of local perturbations in understanding bias, and correcting for discrimination, which is somewhat connected to rate distortion theory. And finally, conclude with some final remarks. So let me start with a brief motivation for fairness and why I find this problem an important problem to look at. Machine learning algorithms are increasingly used in applications of significant individual level consequence. Applications such as recidivism prediction, personal finance, things like automated credit scoring, loan approval, and so on. And things like employment decisions and hiring decisions, like what ZipRecruiter does when you're matching job seekers and job hires. And in these applications, a natural question to ask is, do these algorithms discriminate on race, gender, or some other legally protected attribute? And why do we care about this question? Well, hopefully not only because all of us want to live in a more fair and equitable society, but also because it's the law. If you're a grad student here and tomorrow you go on and do your amazing new startup that's doing AI for human resources or something like that, the United States legislation has very clear norms of what constitutes or not constitutes discrimination. And just to be clear, whenever I say discrimination in this talk, I mean it not in its usual statistical sense, but in its social science sense. Discrimination as a prejudicial treatment of an individual based on membership in a protected group, such as race or gender. And unfortunately, machine learning algorithms can discriminate. A simple example of this, apparently Google changed this recently, but until recently you could go to Google Translate and type in, she is a doctor, he is a nurse, translate it to Turkish, which is a gender-neutral language. It doesn't have gender pronouns. Get that translation and translate it back to English, you will get, he is a doctor, she is a nurse. Why does this happen? Well, hopefully it happens not because the software engineers who developed this application are somehow biased, but probably because the machine learning algorithms that underlie Google Translate picked up biases that exist in the training data and are now propagating those biases at the output. And this bias propagation is particularly concerning when you look at applications such as recidivism prediction. Today in the United States, in many counties, if you're charged with a crime, they're going to take you to the police station, fill a questionnaire with dozens of questions about you, and feed it to an algorithm that will give you a score, which is what is the chance that you're going to recidivize in the near future or not. And recently, there was a much debated, by the way, article by ProPublica that identified certain patterns of biases in some of these algorithms. And discrimination by machine learning has been documented in many other cases, things like facial recognition, natural language processing, and so on. So why do we observe this discriminatory behavior? So one potential option for this is what is known as disparate treatment. And I'm going to take this slide to already introduce some of the notation that we're going to be using in this talk, which is related to the notation that we saw earlier this morning. So you have a machine learning model, okay? You have this model. And you have a set of legitimate decision variables. I'm going to use as an example recidivism prediction, things like age and criminal history. And you also have a protected attribute S. S here stands for sensitive. And if you use this attribute directly as an input to your model to produce an outcome y hat, you have what is known as disparate treatment, right? Because your output explicitly depends on the sensitive attribute. More pervasive nowadays is what is known as disparate impact, where S is not used directly as an input to the model, but features that are correlated with S are used as an input and might lead to a different performance of your model conditioned on different groups. Okay, just to make this a little bit more clear, what this means is that condition on S, right, condition on your sensitive attribute, minority or majority group, for example, the distribution of input features changes. And this change in input distribution might lead to a difference in performance of your model. Okay, yeah.
But it's not just difference in features, right? If I just output like no on all people, it could also be disparate impact.
Yeah, okay. It could be that as well. This is.
I'm not looking at the features.
Yeah. So, and I think that's naturally leads to the next question. So, how would you measure this, right? And usually, it's measured in terms of a difference in average performance between your predicted outcome y hat and the true outcome y, where this true outcome y is something that you don't control. It's given by society. It's given by this channel here, P of y, given x and s. I'll have more to say how we measure this later. So the goal of this talk is to introduce a few concepts that might be useful in fairness and maybe interpretability of these models. Okay, so if you give me a model, the question that we want to answer from the interpretability perspective is, why does this model discriminate? Can we understand a little bit more of why we might be observing bias at the output? And use this information to feed it back and ask, how can I correct for discrimination for a given model? And what I'm going to do today is present a few information theoretic ideas that might be common across applications and use cases that connect these two problems. Okay, and just to make this transition a little bit less jarring from privacy to fairness, Lalita already mentioned this morning. Both setups are, of course, in practice very different. Privacy and fairness, they have different laws that guide them, different consequences in terms of user experience and things like that. But within this very simple model that we'll be looking at, if you squint, you might be able to see that similar mathematical tools can be used in both cases, right? In privacy, we had the private feature, and that was correlated with your data, and your goal is to design this blue box here for which you disclose so that you produce disclosed data. And on the fairness setup, S is your protected attribute that is correlated with your data that you feed to a machine learning model, plus a hat here, you get the decision. And in both cases, you want your Y, right, your output should be somewhat invariant to changes on the underlying S. Right? In privacy, you want Y to not carry much information about S, however you measure that. And in fairness, you want the performance of this model to not change conditioned on S. Okay, so we're going to be talking about fairness. And before I move on, I just want to say a few words on modeling and assumptions and add a disclosure before I go on with the rest of the talk. And this is something I share with my graduate students when they're thinking of working in this area. So right here, we have an information theory cat. You can think about this as a graduate student who is really excited about information theory, or a postdoc who's thinking about new problems to work with. Well, how do you know it's an information theory cat? Well, how do you know that this cat likes information theory? Well, because it gets really excited about capacity results. It suggests that you use scale divergence for everything, for any problem that you have. And it goes on these long tangents about phase transition phenomena and coding problems, and it insists on wearing that free t-shirt that it got from ITA from many years back. And the information theorists understand that joke. And well, this information theory cat now wants to work with fair machine learning, right? And like most information theorists, this cat lives in this Schrodinger-like state in between theory and practice. Right? And the theory of information theory is a theory of well-defined models and abstractions. It's a world of probability distributions and measurable things, IID samples, precise metrics and well-defined groups, clean data, what computational assumptions, right? And so on. But the truth is, when working in fair machine learning, especially from the practical side, you have to take care because the practice is messy, right? When you talk about fairness and bias, you're talking about things like that touch legislation and public policy, individual level experiences, the way people experience discrimination might be very different, things like implicit biases, the groups that you're trying to protect against discrimination might be fluid, overlapping, and hard to define. Data is messy and often small, like you might be observing bias because of hard to identify causal relationships. The distribution that you use during training time changes when you apply your model in test time and so on. Right, so these worlds are very different and one has to take care when you're trying to reconcile both of them. But whenever I think about this, this is a slide I use in class. I think about a quote by David Slepin. Was from his Shannon Award lecture. He was the second Shannon Award winner, the first Shannon Award winner being Claude Shannon. And where, yeah, right? And where he calls theory facet A and practice facet B.
Was it just called the award back then?
I'm not sure, maybe. But well, during his lecture, he says, to the extent that there is some correspondence between facets A and B, we have the miracle of modern science, the deepening understanding of our universe, and the bounty and ease of the technological society in which we live in. And I think the best part of his lecture is one of the best parts is the second part of this quote, where he says, a second order miracle, little recognized or appreciated, is that this miracle could arise from a really ragged fit between both facets. Okay, so, you know, the theory and practice of fair machine learning, there is a challenge in reconciling both views, both facets. I would claim that information theory has done this rather successfully in other areas, in things like communications, for example. But, and now what I'm going to give you is just very few information theoretic tools that might be useful in fair machine learning. But I proceed, I just want to put this caveat here, that, well aware that the practice of discrimination bias is very messy, it's complicated. But nevertheless, hopefully in the next few minutes, next half an hour or so, I can convince you that some information theory perspective can help understand something fundamental about this problem. Okay, so yeah, let's plow ahead here. So a first natural question is, how do you measure fairness mathematically? How can you quantify these things? Right? And the metrics that we're going to be using is something known as group fairness metric that seeks to quantify this disparate impact. So let's return to the model that I introduced in the beginning of the talk. Okay, so we have our legitimate input variables x. You have a sensitive attribute s. S is not used directly as an input to your model, but x is, and in order to produce an outcome y hat that tries to approximate the true outcome y. Right? And let's assume you have a disparate impact. You observe a difference in performance when you input samples from one population versus the other population. So group fairness metrics are usually defined in terms of differences between outcomes and error rates across different populations. Okay, so let me give you a recipe on how to build these so-called group fairness metrics that are used in the fair machine learning literature. And this is based on an excellent tutorial that Arvind Narayan gave at FatStar a couple of years ago. So assume that y and y hat is binary, okay, the simplest case. Then I can get my model and I can feed samples from population s equals 0. Think about that as the minority population, and build this confusion matrix here, the true negative, false negative rate, and true positive rate. And also look at the marginals, right? What is the fraction of that population that I'm marking as y hat equals 1? Like, what is the fraction of the population that I'm marking as recidivist? I can go and do the exact same thing for the majority population, s equals 1. And if you're comparing, for example, the difference of inputs that you mark as y hat equals 1, right? This is what is called statistical parity when you try to equalize these two numbers. You can try to equalize, for example, false positive and true positive rates. And then you get something that is known as equalized odds in the literature, proposed by Hart, Price, and Nettie Cerebral, where you're trying to condition on the true outcome being 1 or 0. You want the probability of marking y hat equals 1 to be approximately the same across both populations. If you restrict to this box, here you get something known as equal opportunity, where you're just looking at the outcomes where the true output is y equals 1. But however you split it, there are combinatorially many metrics that you can define just by combining and comparing these two tables. And there's many trade-offs that you can derive between these different fairness metrics. And in fact, there's quite a few results in the literature of fair machine learning that seek to understand trade-offs between these metrics. And what we're going to do today, what we're going to do next is ask a very simple question, which is how do these metrics change when the underlying distributions are perturbed? Okay, if I were to hypothetically change a little bit the distribution over one of the groups, it's just a thought experiment, how would that influence your metric? And that will say something interesting about potential sources of bias and how we can correct for that. So this is what we're going to do next. Then next, we're going to look at the role of perturbations in understanding bias. And here we're going to be using tools that are found in robust statistics and also in something called Euclidean information theory, where you look at small perturbations of measures and see how that might help us understand disparate impact. Is it clear what we're doing next? Yeah.
Before we perturb things, is it known just how to construct hypothesis tests that satisfy those different criteria?
I'll say that towards the end. Like how can you change a model or process or distort your data and so on. That will be the part 5, like correcting for discrimination. So let's put that question on hold and we'll get there. Any other questions? But yeah, just to be clear in the answer, yeah, there's several methods to do that. And we'll be talking about that in a bit. Okay, so to look at these perturbations, before we perturb things, this is the framework that I'm going to consider. I'm going to make 3 key assumptions. Okay, so the first assumption is that we have a classifier, and this classifier is a black box. I don't care how this classifier is implemented. You can think about this as an API that I feed samples to that classifier, and I get results back. Okay, this classifier is denoted as h of x. It doesn't depend on your sensitive attribute explicitly. You can think about this as the output of the classifier being a belief, a probability distribution, p of y hat equals x. Second assumption is that I'm going to assume that I have an auditing data set, right? This classifier is there, it's implemented, and I have a data set that is sampled from the deployment population where I want to apply that classifier. If I don't have such a data set, it might even be hard to identify biases in this model and so on, okay? So for example, this auditing data set in the recidivism prediction case might be something with samples of race, age, prior count, degree charge, and recidivism for your underlying population. And I'm going to assume that S and Y are binary, just for the sake of simplicity for the rest of the talk. Okay, and so first we have a black box model. Second, we have an auditing data set. The third assumption that we're going to make is that we have a fairness metric. As I mentioned, there are many. The fairness metrics that we're going to consider are based on the metrics that I presented in the comparison of true positive and true and false positive rates. And just to introduce some notation, this first one looks like statistical parity. It uses scale divergence. This one was proposed by the information theory cat. And we're going to assume that we have a target group who has an unfavored performance. You're observing a higher, say, false positive rate or something like that. And you have a baseline group over which you want to normalize the performance for, right? And we're going to make, so the target group, we're going to mark it as S equals 0. You can think about some minority group or a disfavored group. And we're going to assume that Py given XS, the model that produces the true outcomes is fixed, that the distribution of features over the baseline group is fixed, and that the prior P of S is fixed as well. So assuming that all of these things are fixed, you can cast these metrics in terms of one parameter, well, in terms of one distribution, which is the distribution over the baseline group. And what we're going to do next is a thought experiment. It's not something that we can actually go and do in practice, but it's just a thought experiment to see where it takes us, that we're going to ask, how can we find a new distribution over the target group that minimizes a given disparity metric? And by the way, all the results that I'm going to present now also can take into account linear combinations between these metrics. So that gives you things like equalized odds and so on. Okay, so this is the thought experiment that we're going to do. And I'm going to introduce this through a picture. Okay, so what this blue triangle here represents is a probability simplex, just a cartoon that illustrates the space of all possible distributions over input features. The distribution over your target group will be a point here, P of x given S equals 0, over your baseline group, P of x given S equals 1. And if we were to sample from each of these populations, it would induce an output distribution, either over the predicted outcomes or over the true outcomes. So if you sample from P of x given S equals 0, feed it to a classifier, you get a distribution induced over outputs. And the same thing for the true distribution, same thing for P of x given S equals 1. So our goal is that we want to change this distribution, distort this distribution, in order to reduce the disparity over the group S equals 0, the group that's unfavored, right?
Flavio, I'm a little confused over why this is the goal. So maybe you'll get to this later, but why is the interest, like, what, I'm not sure, is it the fact that we're going to think of this as some operation we can perform in real life,
yeah,
like an actual shift in the distribution?
Yeah, so let me explain where this is going. We're going to analyze this theoretically. And then we're going to see that the solution of this is we can actually find these distributions that minimize disparate impact just by doing combinations of models. And then we're going to use that to solve an optimization problem in order to reduce disparity. Okay.
So our ultimate goal is to change the classifier?
No, the classifier is fixed. We're going to pre-process the data before we change the classifier. But
But that is changing the classifier, right? Like you're saying,
Yeah,
when you
yeah.
pre-process the
The
data, you're
results of
going
the
to
classifier.
add a unit.
yeah, okay, yeah, sure.
Create a new classifier, which happens to work by like first doing something with
Yeah.
the data and feeding it to the original classifier.
Yes, yes.
And so your goal, what is the problem you're sort of ultimately aiming to solve? Maybe is the question.
Yeah, so my goal is to understand like how to find this distribution and later on map points from this distribution into this new distribution. Basically create a preprocessor for my group S equals 0 before I feed.
So I feel like that's an intermediate goal. Like you're trying to, but maybe I don't understand. So you're trying to find a new classifier that just does better with respect to
Fairness metric.
Fairness
this
metrics.
particular fairness metric
Exactly.
on this particular distribution.
Yes.
Okay,
Yeah.
good. And now the specific way you want to do that is by pre-processing. You're going to do something to the input features so that this
Yeah.
better this particular metric you fixed is improved.
Exactly.
Okay. Thanks.
Is that clear?
Yeah. No,
Okay.
that makes more sense.
Any other questions? Yeah.
That means you'll be changing your input data or
Yeah, we're going to randomize it. And later on, I'm going to use that as a segue to pre-processing methods in discrimination prevention, of which there are many, like our intervention mechanisms.
Yeah, I guess that's what I was going to ask, but figured you'd get to is like there are lots of proposed ways to
Yeah.
modify it.
And I'll get there, absolutely. Yeah.
All right, great.
Yeah, I'll get there. Anything else? Okay, good. So, again, we're looking at these perturbations because eventually we want to understand how to correct for bias, right? And maybe be able to identify something interesting about why we are observing this disparate impact. And maybe say something about that. So, we're going to call the set of these distributions that minimize a given disparity metric as we're going to name them counterfactual distributions. This is a loaded term. So we use the term counterfactual because it's a sense of thinking what would be the distribution over this group in order to remove a given disparity metric, right? But again, the counterfactual, this term is used in many different ways in causal inference and so on. But all that it means here is that this is the set of distributions that minimizes a given disparity metric when you change the distribution over the minority group or the target group in order to one of the distributions in this set. And you might be wondering, well, why don't I just map this distribution onto P of x given s equals 1? Right? Why don't I make the distribution over the target group the same as the baseline group? Well, that's not necessarily optimal if you're looking at things like false positive rates or true positive rates and so on, because this channel here, P of y given x s, we're assuming that it's fixed. Okay, if you're just looking at statistical parity where you want to equalize the output distributions, you will map this blue dot onto this green dot here. Okay, so next I'm going to say how you can find these counterfactual distributions via local perturbations, and later on I'm going to show how you can use it to do a preprocessing mechanism in order to remove disparate impact for a given metric, and then mention about other methods that do that as well. Okay? So you can find these counterfactual distributions via local perturbations. You can think about that as gradient descent over the probability space. And later I'm going to show you how you can actually instantiate this in practice. Okay? So if you're a grad student in the room, and this is a cool thing to know, how do you perturb probability distributions so that you stay on the simplex? And the way you can perturb it is usually instead of adding an additive perturbation, the easiest way of doing it is adding a multiplicative perturbation. As long as this function has finite variance and zero mean when measured according to P of x given s equals 0, you're still on the simplex. Okay, so as long as this function has zero mean according to P of x given s equals 0. And when you perturb your distribution like this, the output distribution also has a multiplicative form. So we can also write the output distribution as P of y given s equals 0 times 1 plus epsilon g of y, where this g is simply the conditional expectation of f given y. Okay, so this perturbation is mapped into this perturbation via the conditional expectation operator. So just to make this clear, you're looking at multiplicative perturbations over the distribution of your minority group, of your target group, and that maps into a multiplicative perturbation of the output, assuming that these functions are in the space of zero mean finite variance functions of each of these distributions. You can look at the spectrum of the conditional expectation operator and understand how the perturbation of one input distribution affects the output and overall affects your metrics. And I'll have a lot more to say about the spectrum of this guy here. A condition on s equals 0 is missing tomorrow during the privacy talk. Okay, so I just wanted to put a placeholder here. Please come tomorrow and learn more about it. But for now, we're going to do this local perturbation in this multiplicative form. And we're going to call the new perturbed distribution as p tilde time of your original distribution times 1 plus epsilon f of x. Okay, so, and which perturbation should we choose? Well, we're going to do something that looks like a derivative, right? We're going to perturb according to the direction that minimizes a given disparity metric. So when you write these things like this looks like a derivative in the probability space, right? It's directly, these local perturbations, this is a tool that you find, for example, in Euclidean information theory. These are some tools that were used in network information theory and so on. This is also connected to influence functions in robust statistics, right? What an influence function asks is how would this statistic change, your disparity metric, if you were to add just a little bit of probability mass onto your distribution. You can think about this as having a very, very large data set. And how would that metric change if you were to change one sample of that data set? And recent paper, we show that the function that minimizes over all functions f that minimizes your disparity metric, the direction of steepest descent, is equivalent to a normalized version of the influence function. So the question of trying to find these counterfactual distributions, finding a hypothetical distribution that would minimize a given disparity metric, then is mapped to computing these influence functions from data. And how do you compute these influence functions for different fairness metrics? Go ahead, Adam.
Maybe you don't want to spend time on this. I didn't understand where unit variance and zero mean come. Like somehow there's a type mismatch. We weren't
Zero mean
in my brain. Like zero mean over what?
So zero mean over p of x given s equals 0. Because if this function has zero mean, this whole thing still adds up to 1 when you integrate over x. And as long as you're making epsilon small anyways, but as long as it has finite variance, you're also trying to ensure that this doesn't become negative when you perturb. So you're still stuck on the simplex. So again, just rephrasing what I just said, like you're asking how would you perturb the probability distribution so that the resulting perturbed thing is also still a valid probability distribution. And for that, you can restrict f to have zero mean and finite variance, unit variance, because you're making epsilon very small anyways.
Yes, sir. I see where zero mean comes in. I'm not sure I understand why. Now, thank you.
Yeah.
That answered part of my. I'm not sure I understand why variance.
This is just a restriction that we added. You don't have to restrict f variance to be 1. But since you're making epsilon small anyways, and you can just normalize everything. But that's not a necessary condition.
Right, but it comes in on the next slide because you're normalizing the psi function in this specific way.
Yeah, because here we're restricting a minimization to have unit variance, and that's what we're doing. But you don't have to. You can always have a multiplicative constant here because you're making this epsilon small anyways. Maybe you can talk more about that later. Okay. So this is the expression for the influence functions. They're really complicated expressions. I'm not going to go into details here. You can find derivations in our recent preprint. But this is the takeaway of how you would compute these things from data. Okay, like you're trying to find what would be this hypothetical distribution that would remove discrimination. You have, what these complicated expressions indicate is that you can estimate this influence function by 3 steps. First is that you train a black box classifier. You have your black box classifier that you're auditing. You can train a new classifier locally, right, based on your auditing data set that tries to predict group membership given your samples X. And you create a new classifier that approximates just for your baseline group, right? You try to create this well-calibrated classifier, P of y given X, S equals 0. And these are values that you can estimate from your auditing data set. And based on that, you can compute the influence functions that I showed on the previous. You can plug these values into these equations, and you can estimate the influence functions. And how do you recover a counterfactual distribution? Well, we never actually recover the distribution itself. We're not going to get an expression for this distribution. What we're going to get is a set of resampling rates for your distribution over the minority group, a set of resampling weights for your auditing data set condition over your target group, so that if you were to resample according to those weights, you will get something that approximates the counterfactual distribution. And in order to recover it, you can do something like stochastic gradient descent gradient descent on the simplex, where you have a point, you estimate the influence function, you compute the perturbed distribution, and you get a new distribution. We resample your auditing data set according to these new weights, and perturb it, estimate the influence functions again, and just keep doing that, and eventually you arrive at this set of distributions that minimizes disparate impact. And you can actually do this in practice, right? So you can actually go and resample according to this. This is just one example using artificial data. We have more examples in our paper, where as you compute these influence functions and keep estimating, and you can actually arrive at a new set of weights across your auditing data set when you resample according to those weights and feed it to the classifier, that disparity is removed. So,
Question.
yeah.
So in general, the S equals 0 set, so maybe in the recidivism data set is very large, assuming 0 is black, for example, then you are going to sample less from that subgroup.
No.
Very likely that's what's going to happen when you try and make the data set fair, right?
Yeah, well, the question is, how can you use this for model repair? And I'm going to give you one way of using this for model repair. There are many methods for trying to remove discrimination from your model using this counterfactual distribution. And the way you can do this is, just to make our goal clear, right? What I mean by model repair is a set of methods called pre-processing methods, where here is your black box classifiers. You have samples from one group and samples from another group. And your goal is to design something that looks like this. The classifier is still here, but you can locally change your sample, right? So that before you feed it to the classifier, when you look at the average output of the classifier, you reduce disparity. But now we have a original distribution and we have this target counterfactual distribution. How do we map samples from one distribution to the other? You can solve an optimal transport problem, for example. And the optimal transport problem gives you a coupling that you can use to build this preprocessor, right? Where this cost tries to control so that you don't distort your data a lot. And you can solve this optimization problem, try to get this mapping, and then build this preprocessor. And for different fairness metrics, false positive rate, false negative rates, and so on, you can actually apply this approach. Like this is two examples on the adult data set and the Compass data set, where you have the discrimination gap and you follow this procedure. And after you map it to this new distribution using the randomization given, the coupling given by the solution of your optimal transport, and you can actually remove the discrimination for most cases here.
And what's the cost that what you were concerned about? Was this target area under the curve? Or?
Yeah, so this is exactly what I want to mention now. Like you see that the discrimination is removed, but there's some loss of performance here in classification performance. And this loss is connected to, for example, the cost that you choose. So the question is, what is the optimal way of doing that? And in part, yeah.
Before you go there, can you explain why some of the rows don't have 0 in the gaps?
Because there are some cases where you can't necessarily completely remove discrimination. Yeah, we have conditions in the paper where by following this procedure, where the gap cannot necessarily be made 0, because basically your class, yeah.
Couldn't you always resample like just according to the other distribution?
No, because like things like false positive rate, for example, might be different. Yeah.
That's what I was trying to ask.
So we have conditions in the paper for when this, necessary conditions for this being 0, not sufficient, I think. So what is the optimal trade-off between correcting for discrimination and accuracy, right? There are many, many other mechanisms that seek to ensure fairness. Okay, and I would argue that like determining these optimal trade-offs is something that is well within the purview of information theorists. I don't have a solution for this now, but what I want to give you next is just to wrap up the talk, is just a few methods for correcting for discrimination done not just by myself, but by many others. So how would you repair a model, right? And these methods can be very roughly classified in terms of pre-processing and processing and post-processing. Okay, so here's a setup. And by the way, this is a very incomplete list of references. There is a lot of work happening in this field. So I just want to put that, make that disclaimer. So you have your data set, right? And you're feeding it to the model in order to produce the output y hat, right? You may or may not be using your sensitive attribute. Y, of course, the true outcome is not used during testing and so on. So one strategy that you can do is something similar to what we did, right? It's pre-processing. I'm going to produce a preprocessor so that I'm going to somehow distort my data before I use it for training or before I feed it to the model in order to ensure some metric of fairness. Another option is do in-processing, where we change the model itself in order to ensure fairness, right? You might have a logistic regression and try to figure out how to tweak the weights of the logistic regression or something like that. Use some model-specific characteristic. And the third option is post-processing, right? For example, in this work, you can set different thresholds for different groups and look at the output of the model. If it's making like soft decisions, set different thresholds for your decisions and so on, and seek to ensure fairness that way. So tools from rate distortion theory may help us delineate some of the limits of data preprocessing for discrimination prevention, right? And might be able to help us answer what is the optimal trade-off, at least in certain cases where you know the distribution artificially, for example, that you could achieve between fairness and accuracy. So just to make this clear, when you're designing a preprocessor, usually what you're trying to design is something like this. And these are kinds of things that we see in privacy all the time, right? Where you receive a sample SXY, and you want to map it into a new set of samples, S, X hat, Y hat, in order to control discrimination according to your favorite metric. You also want to limit individual distortion, right? Some may call it a notion of individual fairness, right? You want to avoid certain gross deviations. You can always achieve fairness by just producing random outputs, but you might want to ensure that accuracy is preserved. And you might have also some notion of utility. I use the term here utility very loosely. All that this means is that if you're changing the data before you input to the model or before you train the model, you might want the output distribution to be similar to the original one, just so that the model that you learn is not drastically different. Sometimes this model is interpretable. You might be able to say something interesting by looking at it. So when you have these three goals, like maybe your first reaction is to just fit them into an optimization problem. And this is exactly what we did in a prior paper from a couple of years back, together with collaborators at IBM, where you get a formulation that looks remarkably similar to the test channel that you get in rate distortion theory and so on, where if you were to know this distribution P of XY, you can try to find this randomization mapping in order to preserve utility, limit individual distortion, right? Control these deviations that you have. And for a given discrimination metric here, I'm not going to go into the details of what this J means, but you can think about that as statistical parity, for example, in order to reduce this, to control discrimination. And if you know the distribution, you can solve this and to try to receive like what is the optimal trade-off that you get. Of course, we may not know the distribution in practice. You can try to solve this using, for example, the empirical distribution, a type estimate of your distribution, and see how that works. If you use a type to solve this optimization formulation, what you can get guarantees that look like this. This is for statistical parity. This is your utility guarantee. Of course, the distortion is a property of your mapping itself. I just wanted to show this result because you see here that this convergence bound is not that great. It's pretty terrible, actually. It only holds for discrete data. It depends on the probability of the least likely symbol and on the size of your alphabets and so on. And take this chance to advertise Lalitha's talk, where she's going to talk about more refined bounds when you're using empirical estimates for looking at the solution for these optimization problems. But you can actually go and design these, assuming that your data is not that big, you can go and solve this optimization problem and get this distortion mapping and apply it in practice. So again, this is another example with a recidivism prediction data set, the COMPASS data set, where if you get the COMPASS data set is a data set with recidivism information about people that were charged with a crime in Broward County in Florida. And there we consider as the sensitive attribute race. And if you just use that data set, they have the true recidivism outcomes and use that to train a random forest classifier to predict recidivism. You get and use the sensitive attribute as an input to your model. You get fairly good accuracy. And, but you also have a lot of, at least for the random forest that we trained, you get quite a bit of discrimination. Statistical, the gap in statistical parity is pretty high. You can do the same thing just by dropping the sensitive attribute, retrain the model, and see what accuracy you achieve. You have a small loss in accuracy, but you see this red impact is still present here. And these 2 points here are the solution of solving the previous optimization problem using different parameters, control parameters, and plugging it in. And you can see that you can reduce discrimination approximately to the target values of 0.1 and 0.05. And the natural question to ask is, what is the best that you can do, right? What would be the optimal information theoretic limit in this case? And I guess this is more of a call for action, because I don't think we have a crisp solution for that. And in particular, I just want to highlight this result, this paper. This is a paper by Sorel Friedler and collaborators from this year's Fat Star conference, where they did a remarkable and great effort in trying to compare the many different fairness intervention mechanisms, some of which I cited in the previous slides. And as you can see here, this is the test of these mechanisms for different data sets. On the y-axis, you have accuracy. On the x-axis, you have something that looks like statistical parity. This is another example that looks at the same. And you see the performance of these metrics are all over the place, right? I think a natural question would be is, what would be can we create synthetic data sets and analyze the distribution of these data sets using tools from information theory to ask what would be the best that you can achieve in terms of these accuracy discrimination trade-offs?
Can you go back one slide?
Yeah.
So maybe it's terribly down here, but what is this statistic? So you're saying my prediction should be independent of my
Yeah.
sensitive parameter,
Well,
right?
statistical parity, what it says is like, if you look at, you're training a classifier to predict recidivism, and you're asking that the fraction of recidivists for the population S equals 0, and the fraction of the population marked as recidivist for S equals 1 has to be within a certain value of each other, like 10% or difference or 5% difference.
So that's why you say you want to be on the left side of the x-axis.
Yeah. So again, the takeaway here is that there are a lot of mechanisms for ensuring fairness, right? There are many different approaches using neural networks, using optimization, using other methods. I think it would be interesting. It's interesting to ask, like, what is the best achievable trade-off? What is the best that we can do here? What is the benchmark that we should be aiming for? So I'm going to wrap up with some final remarks. There are many other interesting questions to ask in this field. For example, there may be other unobserved latent variables and potentially causal factors that may explain the disparity that you're observing in your model, right? There's a lot of recent work in trying to understand how can we input confounding factors into our analysis. I think another challenging problem is that we're looking at as well is that the disparity in the model output may be due to lack of samples from the minority group during training. Right? It might be the case that you're observing this disparity simply because when you trained that model, you didn't use enough samples from a given population. So I guess quantifying the impact of data set size and diversity on the bias of machine learning algorithms, that's something that I do think information theoretic tools could help. This is just one example. If you do a Google image search, I did this a few months back for a wedding. You're going to get a bunch of brides in white dresses and grooms in a suit, which may not necessarily reflect like the diverse notions of weddings that we have, right? So how can we make sure that our data sets are diverse enough? So if you're interested in working with fairness and testing out some of these algorithms, I do recommend you also looking at the AI 360 toolbox launched by IBM. They have a very nice package where a lot of the metrics that I mentioned and a lot of these fairness intervention mechanisms are implemented. The optimized preprocessing method that I mentioned is also there, if you want to try to test that one out. And I'm going to end with a slightly cheesy note, which is that with big data comes big responsibility, right? Responsibility and privacy, fairness, and transparency. And I do think information theory can help, right? I think there's a lot of important fundamental questions that, of course, it requires modeling assumptions. It might be a little bit disjoint from practice, but it can reveal some fundamental insight that might be design driver for practical algorithms. So this is just some work on this area that's been done by my group over the past year and a half. So please take a look. Again, the code for this counterfactual distribution thing is also on GitHub if you want to play around with it with your own data sets. And yeah, I think I'll end there. Thanks.
Questions? Yes.
Regarding the trade-off you mentioned, the accuracy disparity, I guess, if the distributions are all known, is the trade-off known then?
Well, I think I would say like the naive approach for that is asking like, well, what if I just look at sample by sample like distortion mechanisms and I solve an optimization problem? In that case, if the distribution is known, I can cast it as an optimization problem and see the solution and see what the trade-off is. I think the more interesting question is actually formulated in terms of some kind of operational formulation, right? Where I have a data set with n samples and I'm trying to learn some kind of new representation of that data set so that when I feed that representation to train a model or something or try to estimate something from that representation, I can ensure certain fairness, accuracy trade-offs, for example. And like, especially if you're using representations that are something like a quantization or something like that. I think the other question is like, why would you do preprocessing at all, right? Why wouldn't you just like, once you have a model, why wouldn't you tweak the model or somehow tweak the output of the model? And yeah.
I guess where I was going from is, I mean, yeah, you can imagine like doing some pre-processing or post-processing or kind of model tweaking, but you can also just imagine like a clean slate design where you say this was not a consideration when the model was first created, so let's throw the model out and think about how to solve the problem that we were originally trying to solve with the model, but now with this added constraint in it. And you know, perhaps one place to start would be in the known distribution case, where you know px given s equals 0, x, and so on. And then rather than just looking at regular likelihood ratio tests, which is what you do without any kind of fairness criterion, you have some kind of modified likelihood ratio test, I guess, that would account for that. And then, you know, then we could go from there to the case where you don't know the distribution exactly, you have samples and kind of build on that. But it's like you're saying the distribution is known, then it's known how this trade-off between disparity.
So well, that's one way. What you mentioned, by the way, there's recent work by, I believe, Maya Gupta and Nadi Several and others where they try to add fairness constraints when you're doing gradient descent for training a model. So like having models that are fair already by design. So there is definitely some work in that area as well. Yeah.
What do the schemes, when the distribution is known, what do the schemes look like that kind of give you the optimum?
I don't know.
It depends on the...
It depends. Like I think, yeah, it depends on the. I think this is one of the challenges because even that's why I really applaud the effort of comparing all these different models, because like you look at different papers, sometimes they use different metrics, they use different assumptions, and so on.
So I had a couple of questions, one technical, one not, and I don't know how much time we have. But the technical question was, you mentioned this influence function. Like, how complicated? I didn't understand in that you had there's 3 ingredients you need. You know, I forget what they were. Yeah, stop.
Yeah, here.
So presumably we don't know how to optimally classify, you know, estimate y given x and s equals 0, and if we did, we wouldn't need h to begin with.
Yeah.
So to what extent, like, how do you deal with the fact that you're solving these classification problems, you know, themselves, or you're solving them like sort of just only imperfectly?
Yeah, so this is the reason that we are interested in this. So I guess let me just rephrase your question to see if I understand it correctly. So the question is like, look, you're training this anyways, right? You're training a model over your target group. So why do you care about h of x? at all? Why don't you just go and use that model directly?
That was actually Aaron's question, but it's a fine question, so you can answer that one instead.
Yeah, so the reason is because you can use this to actually audit the model that you have. So the interesting thing, and this is some analysis that we have in our paper, is that you want to see, for example, why am I observing this bias, right? And you can look at these influence functions and aggregate them over features. So for example, one thing that let me give you a concrete example of that. Like, so you're doing recidivism prediction, and you know that one group has, on average, a higher prior count than the other group, right? And at the same time, your model takes prior count heavily into account when producing output decisions, right? So you know that that feature might be a feature that is a proxy, right? And you can, of course, how can you find this in an entirely data-driven way? And these influence functions can be used exactly for that. So kind of like to try to understand why you're observing this and flag individual features that might be serving as proxies for discrimination. And that's actually was our original motivation in our first paper at ICT last year on this.
So just a quick comment. Influence functions usually they kind of measure just first order effects.
Yeah.
I mean, the influence functions will give you a lot of interesting things, but there's something to keep in mind.
Yes.
Yeah, thanks. Absolutely. This is absolutely just a first order effect.
First order.
I guess my question was like a little different. It's like you don't expect to be able to solve these problems perfectly.
Yeah. Oh, I see. So we have bounds on that in the paper as well. So we have bounds of the following form. If you're out of this by a factor of like some epsilon, how does that affect the error in your influence functions? We have some somewhat precise bounds for that as well. And so basically the way it works is that if your error in estimating these quantities or your, epsilon away in terms of total variation, how does that translate to an error in your influence function itself? And we do have bounds for that. We can discuss that offline.
I guess my other question had to do with these different disparity metrics are not mutually consistent.
Yeah.
And it's not even, they're kind of questions about, what most of them look for is to ensure that errors are distributed in somewhat evenly according to some metric across groups. It's not even clear that's entirely about fairness. But how do you take into account the fact that you're degrading the performance of the classifier? If the fairness metric somehow suppose the result of this is that you just make the classifier less. You're showing that the area under your curve for the classifier was going down. All that new error is happening on this one group because that's the only place where you're changing the behavior of the classifier. At that point, to what? How do you decide? How do you think about whether or not this is actually making the system that you're worried about, the social system that you're worried about, more fair?
Yeah. No, I think that's an excellent question, and I think that's one of the challenges, right? Because there are inherent trade-offs between a lot of these metrics. These metrics are not independent, right? By ensuring better statistical parity, you might be sacrificing false positive rate, things like that. And the question is then how can you ensure that if you're correcting for errors on one kind, you're not adding more errors in terms of the other kind? And I don't think I have a concrete, this is how you solve that problem. You choose a metric, you optimize for that metric, another metric might be suffering because of it. Yeah, and this is the nature of these trade-offs. I guess it would depend on who's deploying it and how they would use it. I think the more interesting thing here also is that these influence functions and as well allow you to probe your model and ask what input features might be more important for assuring equalized odds, which input features might be more important for ensuring statistical parity and things like that. But yeah, I don't. For many of these metrics, there's no free lunch. So yeah.
I mean, there's a more philosophical problem. If the original data itself is very skewed, and you're doing social engineering, it's like the the HUD had to come up with this test, right? I mean, then they picked a number. It said 10% had to be for minorities, 40%. So it's just some number that could be legally motivated at some point.
Yeah, but and I think like our role, maybe it's not the best role, but our role in that is kind of like we're the plumbers behind it, right? Like you design the engine of the car, you design safe airbags, but like there's a lot of questions about what are the rules of the road, right? But at the same time, like it's the same thing here. Like you try to create mechanisms that allow you to navigate trade-offs, achieve good trade-offs between different metrics and so on, and then discuss with practitioners how you would how does it even make sense in choosing an operating point for them? How would you choose that, and so on.
Flavio, why not keeping two models? One model that is trained to do well on, I don't know, a minority group, and then another model that is trained to do well on a majority group.
Yeah.
I know you might not have enough data points to train the model for the minority group, but you could potentially think of ways of using the other data points that belong to kind of people in the majority group to train this model.
Yeah.
But then you would still have two separate models, and you wouldn't be compromising
But
utility.
then you're using information that you may not even be allowed to legally use, no?
Yeah. Well, I think like I'm not going to debate the legality of it.
Oh, okay.
Wind up, like you can still wind up with very large
Yeah.
disparities according to any number of measures. Like, yeah, you can come up with examples.
Yeah.
It doesn't. Training separate models doesn't really solve the question of, how do you decide if the models you've trained are like okay?
Yeah. And there's even the question like, can you allow disparate treatment in the sense like, can you, in this case, does someone identify themselves as part of a group to ensure fairness in the model? Like these questions can you even do that in some applications? That's something that's questionable. So.
In some cases legally you can't. Right?
In some cases legally you can. In cases like medicine, for example, you can. In some cases like loan approval, you can't. But now you're doing it in a way to maybe ensure fairness. So would that be okay? I don't know. Yeah.
Okay, we should wrap up, but I'll just ask you one question. Can your models find who paid for college admission or not?
Ask me in a couple of months.
Let's go to our last speaker, Peter Kairouz. Something else.
Yeah.